Good day, guys. Um, Today we're going to carry on with part 4, section 4. And in this section, we're going to look now at, in the previous section, we looked at powers that were positive numbers, x to the power 2, x to the power 3, etc. And in this section, we're going to look now also at exponents that's negative numbers, x to the power minus 2, for example, and exponents that are fractions, and see what happened, and see if it also follow that general rule of us. All right, and we're also going to compare a couple of binomials again, and we will correct some mistakes that I made there about the naming of them, etc. And guys, then so let's start with this section. Thank you. All right, guys. In this section, we're going to continue with this discussion of simplest cases for the derivative. Guys, in the previous section, we looked at case 1 here was about y equals x squared. Case 2, y equals x to the power 3. And so on, and we put all these cases in a table here, and this is what we got. And then we got the general rule for any function y equals x to the power n, then the derivative is equal to n times x to the power n minus 1. All right, guys, so then I'm also, if you read the last sentence here, but the question whether it is true for cases where n has negative or fractional values requires further consideration. So let's look at that now, guys. And then we have two cases here that we're going to discuss in this section. Case of a negative power, like y equals x to the power minus 2. And also case of a fractional power, like x equals a half. So let's start here. Let y be equal to x to the power minus 2. And what we want to do now is we want to see if in these two cases, if it also follows this rule here. Okay, let's see that. Then proceed as before. Instead of y, we're going to put y plus dy. Instead of x, we're going to put x plus dx. You know this process by now, guys. Then we factorized it. So factorization is just the opposite of expanding. Expanding means when you multiply two things together, you get a product. Factorization is just the opposite. If you go backwards, you break it up again. It's like you've got two factors multiplied together here. So why? Okay, let's first look at the factorization done there, and then I'll discuss the reason why you factorized here. Okay, so let's do it here. It's my first version of the factorization. I've done it in a very clumsy, long way to get to this. Here's my answer. You can pause it here and go through this yourself. Guys, there's actually a much easier way to do this. And this is this one here. Okay, we start with that, x plus dx to the power minus 2. And we put that, the round brackets in a square bracket. And then we factorize it inside the bracket. We take out the common factor, which is x, put it outside the bracket, guys. If you multiply the x with everything inside the bracket, then you end up here again. Okay, so, okay, I've done the initial factorization here. And then this is actually your factorization going on here. But then I applied if you look at the exponent laws, the third rule here, a times b, inside brackets to the power n equals a to the power n times b to the power n. Okay, so whatever is inside your bracket, let's make that the a, and the bracket we're going to make the b. So you can put the x to the power minus 2, and then the bracket to the power minus 2 as well. Okay, and this is what you want. Okay, and this is exactly what you got here. That one there, and this one here. Okay, good. Guys, let's go back. Okay, so now you got your factor outside the bracket. You keep it outside the bracket. And then you put square brackets, guys. And then you do this part here by means of the binomial theorem. You apply it to this. Okay. And because this is a binomial, two terms, one term, second term there. And so on. Okay. So how are we going to do that? Let's look at my discussion here. So guys, now you have it like this, factorized. Now the binomial theorem, this is the one that's used in the books, page 137. Okay, and then you apply whatever is this part here, this binomial to the power minus 2. We're gonna apply the binomial theorem now to this, or the binomial expansion, and then we get this. How do we get this? And why did he do it? He put a 1 there, and that immediately makes the a part, it makes it 1. So all the a parts here will become 1. So it makes the expansion here of the binomial a little bit easier. That's the reason I think that he's done that. I can't find any other reason, but let's do it that way. So a is now 1. If you compare it to this, so 1 to the power anything is simply 1. So there's your 1. Okay, and then you see all the parts where there's an a, it will simply be 1. Okay, so then n is minus 2. There's your minus 2. A is simply 1. You don't write the 1. B is this part here is b is dx over x. There's your dx over x. Then 1 factorial is just 1. It's a silent one. You don't write it. Okay, so you see there's a minus there. Now you go, then here you will have a plus. And series like this, series is where you have terms that you add together. And a series like this, they call this a converging series. It will never end. There will always be another term that you can add, but it will become smaller and smaller, and it will converge to a certain value. Okay, so you get infinite. You get the values. The terms here can go up to infinity. They will never end, but it will converge to a certain value. Okay, guys. So let's look at this one here. So that is now this one here. So it's n is minus 2, n is minus 2 again here, minus 2 and minus 1 there. You can take out the minus, and then you make this a plus 2 plus 1, plus 2 plus 1. The minus go in front of the bracket, but there's another minus in front of the bracket coming from this n here. So the minus times a minus is always a plus, and that's why you have a plus here. You follow? So then it's 2 there, coming from here, and 2 plus 1, and 2 factorial is simply 1 times 2, or you can express it as 2 times 1, same thing. And then you've got a b squared, which is dx over x squared. Okay, and then minus again. You see minus and a plus and a minus, and so on, etc. I'm not going to work out this one, but guys, now you simply multiply this factor outside, this term outside the bracket, you multiply it inside the bracket again, and that gives you, this times 1 gives you x to the power minus 2. X to the power, any x, or when you've got a term underneath your division line here, if it goes above the line, because x is also x to the power 1, and if it goes above the line, it becomes x to the power minus 1. Every time something moves from here to here, the sign changes. From here to there, the sign changes of the exponent. Okay, so x to the power 1, it becomes x to the power minus 1. And if you multiply that with x to the minus 2, x to the minus 2 times x to the minus 1 gives you x to the minus 3. You add them up. Okay, there's your minus coming from there, and there's your 2. And don't forget the dx there, no? The dx. Okay, this is your second term. Let's look at the third term, guys. So here you've got x to the power x squared, because everything inside this bracket is actually squared. So x to the power 2, if it comes above the line, it becomes x to the minus 2. So x to the minus 2 multiplied with that x to the minus 2 gives you x to the minus 4. You add the exponents together. Okay, your exponent laws, guys. Then this 1 times 2 is 2. This cancels with that there, the 2 there. Whatever is left here is 3. There's your 3 there. And then you have dx squared here. Okay, that is your third term. We're not even going to look at that one there, guys. And here are your terms. All right, guys, I just want to mention something about the binomial theorem. I've made a small mistake in the previous section. I called this the old binomial theorem, and I talked about the modern binomial theorem, this one here. Guys, that was actually incorrect. I read up a little bit more about this, and this is actually called the usual binomial theorem, and this is where you use your n here is positive numbers or 0. Okay, and you will see that your terms always they terminate. It doesn't go on forever, it terminates, and so on. Okay, the one that's used in the book, this one here, the one that's used in the book, page 137, this is actually the general binomial theorem, and it comes from, if you go to Wikipedia, guys, and you look it up there, you will see, if you look at at Wikipedia, at the binomial theorem, it will start out like this, and guys, then it gives you your usual binomial theorem. It doesn't call it here usual, but in another part I will show you, it talks about the usual binomial theorem. This is where you have the n as positive values or 0, and you see non-negative powers. It's actually integer powers. Okay, n is bigger. N, they stated here as n, the exponent there is bigger than or equal to 0. It's an integer, and this is called your usual binomial theorem. All right, and it gives you these ones here, you guys, this binomial expansions here. You see these ones here, and you see every time the terms terminate, they don't go on forever. All right, depending on your n there, your n there, your n there, etc. Okay. And then if you go down a little bit further, where did I show it? Yeah. The one in the book is this one. And this is actually so-called general binomial theorem. And Newton, guys, Isaac Newton, he generalized the binomial theorem and actually included all the other values of n. In this case, he used the r here, there's an r there. It looks similar to the other one, but in the other case, and you'll see they talk about the usual binomial theorem referring to the other one. We'll discuss this now. But you see here, the k goes not from 0 to n, it goes from 0 to infinity. Okay, so the terms that's added here goes on to infinity. It doesn't stop, guys. And okay. So they use the r here instead of an n. That doesn't matter, guys. Okay, but r is okay, they say here, when r, let's try and read this. When r is a non-negative integer, in other words, 0 and 1 and 2 and 3 and 4 and so on, positive numbers and 0, the binomial coefficients for k bigger than r are 0. So what do they mean by that? And this is the case of the usual binomial theorem, the one I mentioned just now, which yesterday I called it, or the previous section I called it the modern binomial, but it's actually the usual binomial. So when is k bigger than r? Because here k is 0, here k is 1. This is your first element, this is your second element, your third element. Here k is 2, and here k is 3. So let's say, for example, that r is 2. So x plus y to the power 2. Okay, squared. Let's look at that one. Then r will be 2. Okay, so when is k bigger than r? It's here at the third term. This is your 0th term, your second term, your first term, your second term, and your third term. Here at the third term, k is then 3. Is bigger than 2. We're going to look now at the case where x plus y is to the power 2. So what happens then? Here at this term here, okay, where k is bigger than r. So then r becomes 2 minus 2 is 0. Okay, and then what happened with this whole term here? It becomes 0. Because 0 times anything is still 0. Okay, and then all the other terms following on this will have a r minus 2, which will be 0. So all the other terms will fall away. So this will fall away, and then you end up with only these terms here. Okay, and this is the case in the previous one where I said that your terms end. They don't go on forever. Okay. Okay, so let's carry on reading here. So all the other terms become 0. So this equation reduces to the usual binomial theorem. So this is when r is a non-negative integer, a positive integers. And there are at most r plus 1 non-zero terms. Guys, you can work this out yourself. It works out like that. For other values of r, the serial typically has infinite, for other values of r. Now guys, what is the other values of r? That is the negative numbers. That is the, I hope you can read, this is a bit small, sorry guys. Other value, r actually stands here for real numbers. That is your negative numbers, that's your fractions, all those numbers. The series, this is called a series. The series typically has infinitely many non-zero terms. Okay, so in the other cases where you have x plus y to the power minus 2, etc., x plus y to the power a half, etc., you have, you have infinitely amount of non-zero terms. Okay, and this is the, you can see if you compare this one in the book, compare it to this one here, you will see it's the same thing. This one here to this, it's the same thing, guys. So that is the generalized binomial theorem that is used in the book. Okay, so just to make that clear for you, sorry I talk about this now for a long time, but okay, let's carry on, guys. Okay, so now we you could also have applied the binomial theorem without factorization, guys. The only reason why I factorized it here is because I think that you wanted to make it simpler, the factorization going on, the expanding going on here with the binomial theorem. But if you simply use this one here that we discussed just now and apply it directly without factorization, you also get the same answer. You can pause the video and go through this yourself. Do it by means of this one here, okay, and you will see, you will get this. Okay, I'm not going to go through every little thing, but you will see the answer here, this one here, is exactly the same as this one here. Okay, exactly the same. So you don't have to do this factorization. All right, as far as I'm concerned, guys. Good. Let's look now at the other case. Okay, we're not done with this. Sorry. Okay, so you end up with these terms here. I hope I don't let you astray with all my discussions there, but okay, let's carry on, guys, as quick as we can. Okay, so guys, neglecting the small quantities of the higher orders of smallness, the second order of smallness, the third order of smallness, you can strike it out. You know the process by now from the previous section. You strike it out, guys, and you're only left with the other two terms there, which is these two here. Okay. And again, we're going to say, okay, but we started out with y equals x to the power minus 2. Okay, so instead of y, we're going to write x to the power minus 2. And then we cancel them. Cancel then with that one with that one. Okay, and then again, you're left with whatever is left there, the dy and the minus 2 x to the minus 3 dx there. Okay. And then you divide again with dy left and the right of the equation sign, and then you get the derivative here equals minus 2x to the power minus 3. And this is in accordance with the rule, the general rule. You have the general rule, y equals x to the power n, then dy over dx equals nx to the power n minus 1. So if you start out with your y equals x to the minus 2, then dy over dx equals minus 2 in front, x to the power minus 2 minus 1 is minus 3. Okay, and this is exactly what you got here, guys. So the general, you can still follow the general rule with negative exponents. Good. Guys, okay, let's look at the last case here now. A case of a fractional power, y equals x to the power half. Guys, we're going to follow the same pattern. Again, he broke it up here. There's your y plus dy, there's your x plus dx. And again, he broke it up here into 1 plus dx over x. I think because you want to make the expansion simpler. Let's go there and look at how it's done it here. And guys, you can do your factorization to get it to that. You can do it two ways. You can make anything to the power of half. Okay, so if you start with this, you want to factorize this. Anything to the power of half, you can put it as a square root. Okay, this is a square root. And then you can factorize inside the square root. Okay, like that. You take out the common factor x, and now you can break up the square root like this. Okay, and then this again you can write it as exponent, the square root of x as x to the power half. It's the same as that, and then the 1 plus dx to the this one. You can write it like that, and this is what you want. Okay, but it's simpler just to write it as x plus dx to the power half, and you keep the to the power half on the outside, your square brackets, you factorize inside the brackets, and you simply express it again as you use your second rule again there of the, sorry, your third rule of the exponents. Where was that? The third rule here. You use again that rule, and you end up with this. Okay, and this is what you want, and this is exactly what you got here. X to the power half times in the bracket 1 plus dx over x to the power of half. Okay, and then you do your expansion again, guys. Here I'm just gonna, you can pause the video here and do it yourself, guys. This is really not difficult. You keep the factor outside the square bracket, and you do the expansion with the binomial theorem here, this one here. Okay, and you go like this, and as I say, pause the video here and go through this yourself. This is what you should have. Okay, and then you multiply the x to the power half, again multiply it with everything inside, and x to the power half you can write as the square root of x, the same thing, plus a half times x to the power, x here becomes x to the power minus 1 if you take it above the line, and then if you multiply it with x to the power half, then it's half minus a 1. Half minus 1 is minus half, and then you bring it below the line again, and then it becomes x to the power half, which is square root of x. And so you carry on, and here you've got x to the power 2 below the line. If you bring it above the line, it's x to the power minus 2 above the line. Multiplied with the x to the power half here gives you x to the power, okay, so you can leave the 1x here and bring the other x, you can bring up above the line, that is x to the power minus 1. Then you multiply it with that, it becomes x to the power half, minus half, and you bring it below the line, it becomes x to the power half, which is this one here. Okay, and guys, like this here, like I've showed you in the red. Okay, something like that. All right, and this is how you get this third term here. And the 1 to the power, 1 over 8 here is coming from a half minus a 1. That gives you your minus here. And a half times a half times another half gives you 1 over 8. Okay, and like that. Okay, guys, and this is exactly what they got here. And now again, guys, let's go back there. Now you can, here it is written like this. And plus terms with higher powers of dx, we're not going to use this, so we don't have to write it, guys, because it says here, subtracting the original y equals x to the power half, you can make that one y equals x to the power half, and you can, that one now cancels with this one here. Okay, and you're left with, and you can eliminate all the higher powers of smallness. Now, the second order of smallness here, which you can strike out, etc. And you're left with that term there, dy equals a half dx over the square root of x. And again, you can write this is x to the power a half. If you bring it above the line, it becomes x to the power minus half. The sign of the exponent changes if you go from above the line, below the line to above the line, or vice versa. All right, you follow that. So then you have here your answer, dy equals half x to the power minus half times dx. And again, you divide with dx left and right. You know the process by now. You end up with the derivative here equals a half x to the power minus a half. Agreeing with the general rule, guys. Again, agreeing with the general rule. Let's write the general rule again here. Y equals x to the power n. Then dy over dx equals nx to the power n minus 1. So if you start with y equals x to the power a half, then your answer should be dy over dx equals a half, put in front, x to the power a half minus 1. What does that give you? Minus a half. All right. And exactly your answer here. Okay, so it also follows the rules. Wonderful, guys. Wonderful. Guys, summary. Let me see if I left out anything here. I think I mentioned all I wanted to tell you guys. Yeah, again here, you guys, you could, I don't know if I mentioned it, but if you apply the binomial theorem directly, it wasn't necessary to factorize like this here, this factorization that was brought in here. It wasn't necessary. If you apply the normal binomial theorem, the general binomial theorem that was used in the book, this one here, if you apply it directly, you can use this one here, the general binomial theorem devised by Isaac Newton. This one here that we discussed, if you apply it directly without doing the factorization, you end up with the same answer. You can pause the video here and go through this yourself. I don't know if I mentioned this before. It will give you exactly the same answer as here. Okay, the same thing here. You don't have to do this factorization. You can just simply apply the binomial theorem directly. It will give you the same terms here, the same terms as in this case here, where you did the factorization. All right, guys. So let's just look at the summary here. Then we're done. Summary. Let us see how far we have got. We have arrived at the following rule. To differentiate x to the power n, any function x to the power n, multiplying by the power, and you multiply by the power and you reduce the pi by 1. So giving us n times x to the power n minus 1 as the result. Our general rule. Okay, guys, we're happy with that. Guys, this is the first section where we have some exercises here. I'm not going to do the exercises here in the video. It takes too long, of course, but let me do the first one quickly, just to start you off. Guys, there's your general rule again. And you first one here, y equals x to the power 13. What is dy over dx? You know it by now. You're clever by now. 13 x to the power 13 minus 1, which is x to the power 12. 13 x to the power 12, your answer. All right, so you can do the others. Guys, in the videos, I've also put these videos on my website, and there I've given you the answers. The worked out answers, fully worked out, will be in my website, where you can compare it with your answers and so on. All right, guys, thank you. This is it for this section.
All right, people, we're done with section 4 of part 4, and we're actually done with part 4 now. And we look at all the cases of the exponents, not only where the exponents are positive numbers that we looked at in the previous section, but also in this section where the exponents are negative numbers or fractions. And we're happy it follows the rule, that general rule of us. Actually, in all the cases, all the real numbers, even non-real numbers, it does follow this rule, and so we're happy with that. Guys, and we also compared some binomials there, and I hope I didn't confuse you guys with that too much, and that you followed everything and that it was interesting for you. All right, it's always good to learn extra things about mathematics and so on, so trying to make it interesting for you. Good. Guys, in this section or in this part, we finally get to exercises now, so we're going to start doing exercises. So guys, I will encourage you to actually go and do these exercises, and you will find the fully worked out solutions to these problems on my website. I've put it there underneath this video, and so you can go and have a look there. Guys, in the next section, or the next part 5, we will start looking now at constants, when you bring in constants into the function, either an added constant or maybe a constant that you multiply with the function. What happens then? So it's getting interesting all the time. Thank you.